everybody. This is the next astronomy set of lectures, which are going to be talking about the bigger astronomy instead of the local astronomy where we're focused on the moon, the phases, eclipses, tides, and things that are happening astronomically very close to us. Now we're going to start taking bigger steps. The first step, of course, is to move out into the solar system. In front of us here on this slide, you see a ridiculous picture. The reason it's ridiculous is that if you were to look at the sun at that scale, you wouldn't be able to see the planets. You might be able to see some little dots, but certainly you wouldn't see the planets like that. Everything is out of scale here. The sun is huge, and the planets are very, very tiny in comparison. And that's important to understand because otherwise you can't really understand how things work in the solar system. The sun is extraordinarily massive. Almost all the mass in the solar system is in the sun. A fraction of a percentage is in the planets. So it makes sense then, with all that gravity associated with that mass, that the planets are all in orbit around the sun. And those little circles you see are representative of the orbits. So the first thing we need to do is take a look at what orbits really mean. Okay? So all the planets go around the sun in paths that we call orbits. All orbits are in a special shape called an ellipse. Now, this is a mathematical shape, and an ellipse is sort of like a circle that's been squished. In fact, a circle is an ellipse, and a straight line is the far end of the ellipse. So your standard ellipse looks like a squashed circle. Means that as you're going around the sun, sometimes you're closer to the sun than at other times. So the sun is in a special spot in the ellipse called a focus. There's another focus at the other side of the orbit. Nothing is in that, however. That's just a mathematical point. It's as far from that side of the orbit as the sun is from its side of the orbit. Let's talk some geometry of orbits. We define an orbit by two things. First is the distance between those two focal points, those two foci. We measure that distance between them. And then we consider the length of the longest line that can be drawn within that orbit, within that ellipse. That longest line is called the major axis. There's the formula. Eccentricity, that's a measure of how squished the ellipse is given by d over L. Now we just need to define those. D is the distance between the foci. L is the length of the major axis. So that simple formula will give you a number that represents the eccentricity of the ellipse. So if we look at a quick drawing of it, you would measure the distance between the foci. That's little d. And then you'd measure the length of the major axis, and that's represented by a capital L. So how to calculate eccentricity? If you were doing this on the earth science lab exam or something like that, you would do it this way. First, you measure the distance to the nearest tenth of a centimeter between the two foci. So if it came out to be 10 centimeters, you wouldn't write 10 centimeters. You'd go 10.0 centimeters. Yeah, good. Then you'd measure the distance across the ellipse, which is the major axis. It's the longest part of the ellipse. Both foci should be on the line you're measuring. Again, measure that to the nearest tenth of a centimeter. So first you write the equation, E equals d over L, substitute the numbers with the units. You have to have the units for full credit. Then you solve. Notice the units cancel. Centimeter over centimeter would cancel. Now, this is for a piece of paper in front of you. If you wanted to measure eccentricity of actual orbits and things, you need to call an astronomer or stay in school and become one. So once you have measured that, you would round that number to the nearest thousandth, at least for the Earth Science Regents exam. Let's talk about what eccentricity actually means. In terms of the numbers, the closer you are to zero, the more circular the orbit is. Now, if you look at the number 0, it looks like a circle. This is easy to remember. The closer you are to 1, the more elliptical the orbit is. Okay, and as a matter of fact, once you've squished the ellipse all the way down, you actually have something that looks like the number 1. So if you look at the Earth science reference tables, you can see the eccentricities of the planets. Notice which is most circular and which is the least circular on your scheme for planet data on your reference tables. If you notice the Earth, the numbers for the Earth, the numbers are very close to 0. The Earth's orbit is quite circular. And if you think about it, on our trip around the sun, takes a year, have we ever seen the sun seeming much, much larger or much smaller? We know the sun actually does change size, but I've never noticed it, and I doubt you have either. We are in a very circular orbit. Otherwise, the sun would appear to change size. An amusing thing is, when are we closest to the sun? Now, of course, there's some people who, without any earth science knowledge, think that we're closest to the sun in summertime and farthest from the sun in wintertime, which is an absurd notion because when it's summertime here, what season is it in Australia? Well, everybody knows it's winter in Australia. So are we suggesting the planet rips in half and half goes close and half goes far? That just doesn't make any sense. So close or far does not have anything to do with the seasons. As a matter of fact, we're closest to the sun on January 4th. All right, but the southern end of the Earth is tipped towards the sun then. If this was the sun, this is the southern end of the Earth. That's tipped towards the sun. The southern end of the Earth has a lot of water on it. Huge amount compared to the northern end. A lot more water. And so the extra sunlight hitting the water absorbs it. It doesn't make that big a difference. So we're farthest from the sun on July 4th. But then we have the northern hemisphere pointed most towards the sun. And because there's a lot more land on the northern hemisphere, that heats up much more. So those two effects sort of balance each other out. So even though we get about 7% more intense sunlight on January 4th than July 4th, it really ends up not making that much of a difference, just because of the way the Earth is laid out in terms of water and land. So getting out into the solar system a little bit more, we have the planets divided into 2 logical groups. The first are the planets closest to the sun. These are the terrestrial planets, the rocky planets. You can tell you're on a terrestrial planet because you have someplace you could land. Mercury, Venus, Earth, Mars, these are all planets with hard surfaces you could land on. They're mostly made of rock and metal because when the sun first turned on, before the planets had formed, it blew away all the lighter elements, the gases and ices and things. It blew them far away. What was left close to the sun was the rocky stuff. We assume that's why the rocky planets were formed there. The other planets are known as the Jovian planets. These are the gas giants, Jupiter, Saturn, Uranus, and Neptune. This is where the gas and ice all went. Also, rock and metal could condense out there too, but so much more stuff was available out there where the sun had blown it that the gas giants could form. Now, you might be asking, what about Pluto? Well, Pluto really belongs to the most volatile substances which got blown furthest from the sun. So that's really not a planet. It's more in the field of comets. So the Jovian planets, huge planets made of gas with a small liquid or solid core. We're not quite sure about the cores of them. Let's just talk about the rocky planets. Mercury has always been compared as being very similar to the Earth's moon. Neither has an atmosphere. So without any atmosphere, there's no erosion, there's huge temperature extremes, no chemical erosion, no chemical weathering. Um, this all just stays the same. Those surfaces are billions of years old. Venus is hotter than Mercury. Even though it's farther from the sun, it's hotter due to a runaway greenhouse effect in its very thick atmospheres. Greenhouse effect can get very, very serious. Mars has a very thin atmosphere of carbon dioxide, and it's cooler than Earth. It's quite chilly on Mars. There's a picture of Venus. We have completed a wonderful mission where we orbited Venus for a number of years and took spectacular imagery of, I'm sorry, orbited Mercury for a number of years and took spectacular imagery of that beautiful planet. Venus. Venus has a stunning atmosphere, super thick. It's 100 times thicker than Earth's atmosphere, makes it very hot on the surface. You can never see the surface of Venus from the outside. All you ever see is cloud cover. Well, what's that? This is the biggest rock we know about, at least in our local solar system. Right there. Biggest rock we ever knew. You want to know what the rock is? It's us. There it is. Beautiful planet. This is a picture from the last time humans were a distance away in 1972, coming back to the planet. If you take a look at that after a course in Earth science, hopefully you can see a few things. You can see 3 mid-latitude lows, mid-latitude cyclones there. Obviously in the mid-latitudes, we're south of Africa here. You can see Madagascar breaking off of the east coast of Africa. Plate tectonics is pulling that away. Hopefully you can see the plate tectonics right in front of you there. At the bottom of the Earth, you see the big patch of white. That's Antarctica. That's a lovely picture. That's the Earth and the Moon. The Earth and the Moon are so large in comparison that they're very often considered a double planet as opposed to a planet and a moon. All the other planets, their moons are tiny in comparison to the mass of the planet. Not so with the Earth and the Moon. Earth and Moon are too similar in size to be typical of planet and moons. So we consider Earth special. Earth is special. It's the only planet that appears to have abundant liquid water at its surface. It also has abundant free oxygen, which is continuously refreshed by green plants. The presence of liquid water may be a prime reason for the development of life. Why else is Earth special? Pretty sure Martians aren't studying us. Yeah. We have the development of life in huge quantities, in big life on this planet. Earth is special. One of the best pictures ever taken was this picture of Earthrise above the surface of the moon. When we went to explore the moon in the Apollo missions, we anticipated we'd learn a great deal about the moon, and we did. But perhaps one of the most significant things that happened to us was what happened just with this picture. Seeing the Earth as a distant oasis of life in space, surrounded by nothing that we would be able to survive. The surface of the moon is a void, sterile, incapable of supporting life. And there's the Earth at a distance. We take a look at Mars. We have a lot of spacecraft working Mars right now. We have a number of orbiters. We have a rover still working on Mars. We've had 3 others before that. We have another rover coming in 2021. And Mars is a fascinating place. It could be Mars was once a planet that held life. It might still hold life. There's some tantalizing evidence that there may be something going on biologically on Mars, but we have yet to sort all that out. Maybe in the near future we will find out. the answer to the question, is Mars currently alive? And was Mars once alive? A lot to go. If we take a look at the gas giants, they are huge in comparison to the rocky planets. They have no real surface. The gas simply increases its density as the depth increases. You could never land on a gas giant. There are moons around all the gas giants, generally dozens of moons. Some pretty interesting moons around the gas giants. The Lord of all the planets, that's Jupiter. If you added all the mass of the other planets together, it wouldn't even equal half the mass of Jupiter. It is a stunning planet. You see the great red spot on it. We've been watching that lately. The great red spot has actually been shrinking in the last few years. You see a black dot on it. That's a shadow of one of the moons, one of the big moons of Jupiter. You can see how tiny the moon would be in comparison to Jupiter, unlike Earth and its moon. But the moon is not visible in this image. Next gas giant out is Saturn. Saturn has a very low density. If you could find a really big bathtub, it would float. Very low density. You can actually see, because of its low density, notice it's not a sphere because it's spinning so fast. That oblate spheroid has really taken off on Saturn, and it has a very squished appearance. Uranus, early in its history, appears to have been knocked on its side. Something very violent happened on Uranus. And Neptune, the farthest planet from the sun. We thought Neptune would be pretty boring. Turns out in the atmosphere is the fastest winds in the solar system. Now, if we go further out, we come to Pluto and Charon, its sister. You can see they're quite similar in size. They would be sister planets more than Pluto having a moon. And they're superimposed on the background of the United States, just to give an example of they are not big. One of the reasons they were kicked out of the Planet Club is they are just very, very small in comparison to all of the other planets. So some other things you'll find in the solar system. We find asteroids. In a belt between Mars and Jupiter are huge numbers of rocky objects called asteroids. They range in size from tiny to 600 miles across. Some may occasionally cross Earth's path, and if Earth happens to be there at the time, that would be one of those things that show up on your geological reference tables as a new era. Let's hope that doesn't happen soon. The largest asteroid is Ceres, and here's an image of it. Of course, what caught people's attention right away are those two dots in that crater. People were wondering. Of course, everybody starts thinking alien life, and we're pretty silly when it comes to things like that. It's much more. You get a lot more traction if you think what natural processes might cause that. And inside that very large crater, it appears to have maybe been some water that came out and created salt flats there. So some interesting stuff happening even on the asteroids. Meteors, objects that fall through Earth's atmosphere. Most are vaporized, but some are large enough to hit the ground. And here's Meteor Crater, Arizona, where it hit the ground. This isn't that old. If it was very old, we wouldn't see it. Erosion on Earth removes all things like that. We have had many impacts of meteors, but they don't stay. Earth erodes all evidence. So while we're talking meteors, we ought to talk shooting stars. When you see a shooting star, you're really seeing a sand-sized object, usually not much bigger than that, hitting the thickening atmosphere at huge speeds, 25 to 75,000 miles, speeds like that. 25 to 75,000 miles an hour. Think about that, how fast that's going, and it hits the air. When it hits the air, it shocks the air molecules, and it makes them all momentarily glow. That's what you see. The dust was almost always, once part of a comet. This is why we get meteor showers. The comets leave these dust trails, and when the Earth in its orbit goes through a dust trail, we get meteor showers. You could predict them. So that comet trail is just filled with dust particles. Look at that, some shooting stars. If you leave your camera open when you're having a bunch of shooting stars, you might get something like that. Notice they all appear to come from one central spot. That central spot, then, whatever constellation that is, that's what we name the meteor shower based on. So you might have the Lyrids, which would all seem to originate from the constellation Lyra. So other things out in the solar system, comets. Well, the lightest gas was pushed far from the sun after it formed, condensed into dirty snowballs several miles across. We call them comets. When they come into the inner solar system on very elliptical orbits, the sun vaporizes some of the material and produces a vast moving cloud with a huge tail, which stretches out for millions of miles. So there would be a comet. We haven't had any comets lately, not in your lifetime. I had waited a long time before I finally saw some comets, and we had one comet come in and then another the year after. So got to see two beautiful comets. They seem to sit in the sky. They move. You can see night after night. They change position against the background stars. But while you're looking at them, they don't whoosh across the sky. They just seem to sit there. Notice they have two distinct dust trails. One, the bluish one, that's the ion trail. Those particles are charged, and they are really affected by the solar wind, and they go exactly opposite from the sun. The other particles are also pushed by the solar wind. That always pushes outside, opposite from the sun. Even when it's going around the sun, the tail doesn't stream behind it. The tail is pushed, so it's moving away from the sun. But here, because it's not charged, it also has inertia, and that carries it in a somewhat separate path. Another comet, notice that dust trail, or the two dust trails. We got to talk about the sun. The sun is the nearest star. It's a real star. A star is a luminous object creating its own energy through the process of nuclear fusion. Four hydrogen atoms fuse together to form a helium atom. We'll talk about that. Our sun is an average star. Others are much larger and others are much smaller. Our sun is also in the medium range of temperature for stars. We've been having our sun burn for 5 billion years, and it's anticipated it will continue burning for another 5 billion years. There is our sun in one particular wavelength that lets us see the cooler parts of it. You get a lot of detail. When you look at some of the more energetic wavelengths of the sun, you get to see this. The sun is wildly sculpted by magnetic fields. So it has quite the distinct look when you look at it in ways that can see those magnetic fields. So we consider outside the solar system, way past the Jovian planets, there's the Oort cloud, a huge repository of comets. Beyond that, nothing. Nothing for vast distances. The nearest stars are much farther than anyone could ever imagine. It took us ages before we ever began to understand the size of the universe around us. Thanks for watching.